algorithm analysis. This module will probably take us a week or two, depending on how much we do, how many examples we do. But to get us started, I wanted to revisit basically the same, kind of a very, very similar example to what we looked at when we looked at the list data structures that we developed. I've got an experiment set up here where we are creating 1,000, or this is tunable, so 1,000, 10,000, 1 million, whatever, random integers, and we're adding it to this list. Initially, I've got an array list, and now I've switched over to using the Java array list and linked list implementations. And then I start a timer, and I go over that list using get the ith element, and I sum them all up. And I'm not really interested in the result. I'm interested in how long it takes. And so when we do this with an array-based list, right, we go 1,000. Well, it goes by lickety-split. It's not even noticeable. 10,000, it starts to get measurable, 0.001 seconds, but still not noticeable. 100,000, right? Then it doubles. Again, still not noticeable. That could be just a sampling error, right? And so we see that this starts to go up. 10 million, right? Then it gets noticeable, right? But it's still very, very, very quick, right? Now let's go ahead and ramp this back down and go to a linked list implementation. Now initially it's going to be very fast, just like an array-based list. It's going to be 0.001 seconds here. When I kick this up to 10,000 though, instead of staying very, very low, we start to see a noticeable difference. This is now like 50 times as slow. If I go up to 100,000 here, now it becomes excruciatingly slow. This is actually going to be about 4 seconds, 4 or 5 seconds. That's about 100 times as slow, right? If I go up by another order of magnitude here, 1 million, and if the same trend follows, that it's going to be 100 times as slow, then 5 seconds times 100, that's 500 seconds or thereabouts. We'll go ahead and run it in the background here. Fortunately, I've already done this experiment, right? And here are the results. So on the x-axis here, of course, you'll see that the list size goes up by tens of thousands, right? That 1,000 over here is actually 1 million. Yeah?
Did you do this yourself, or do you have just something log it and then just like...
I did, oh, well, I automated it. Yeah, I set it up so that it would do this. And the blue samples are my times, right? When you get up here to 1,600,000, between 500 and 600, that's about 9 minutes, okay? So if I let this go, it would be about 9 minutes, about what our prediction would be, okay? Now the red line there is what's called a quadratic regression. You've probably heard of linear regressions, right? If you've got a bunch of data points, you want a linear function to fit those data points, right? Here, it's definitely not linear because it's not a straight line, right? It's definitely, it looks quadratic, and so I threw this into a quadratic regression, and I got this red line out of it, right? When I did that, I got something that looked like this. Let me go over here now, right? So that coefficient out there, right? We've got n squared plus, this is just a general form, a x squared plus b x plus c, right? That's going to give you a general quadratic equation here, or quadratic polynomial. That coefficient sitting out front there, that's capturing how much each operation actually takes, how long each operation takes. In other words, adding one number to another number, it's extremely fast. It only takes 0.00016 seconds or something like that, right? So each operation is really, really quick, really, really fast. But you're doing n squared of them, right? And then this is a little bit of an adjustment, and this 9.78 seconds here is another adjustment to this adjustment. And look at how closely that quadratic regression fits. In fact, I think that I've got a coefficient here of 0.994. It doesn't get much better than that. A perfect fit would be 1, right? And then a perfect negative fit would be, -1. So, this is almost exactly what we've measured here empirically, okay? So let's use that, because I'm not going to sit here and wait for it to execute on even, say, 1 million. If I did it for 10 million, how long would it take? So again, for 1 million here, it's going to take about almost 10 minutes. If I extrapolate this and put this into Wolfram Alpha or something like that and compute it, I'm going to get that 10 million elements is actually 17 and a half hours. Right? So if I actually ran that, I would expect it to run for almost all day. If I went up another order of magnitude to 100 million, it's going to be 74 days. And you start to see these epochs going up and up and up, hours to days. What about 1 billion? Just give me an estimate. A month, 2 months? I mean, we're already up to almost 3 months.
At least a couple of years.
At least a couple of years, 20 years.
Yeah.
Right.
The difference between a million seconds and a million.
Yep, 100 times as slow, right? Now, let's understand why that is. In fact, before we do that, but I also graphed the linear version of it, but I left it out of that graph because it would not even register, right? So up to 1 billion here, it's only going to take 2 minutes when I use not a linked list, but an array-based list. In fact, I'll show it to you. 1 million here, remember that what that was? I think it was like 0.5 seconds or something, like, or 0.0 seconds. There we go. 10 million is going to be a little bit more registerable. There's 100 million, right? And that was about 5 seconds. Now, if I go up to 1 billion, I can almost guarantee you that it'll take about 2 minutes, but we're going to run out of memory before that, right? So it will run, if I had more memory or gave the Java virtual machine more memory, it would actually succeed. But we're going to end up running out of memory here. Right?
Oh no, what you say?
Yeah, out of memory. The Java heap space was set to some ridiculously low number. 1 billion here is going to be 4 billion bytes, which is going to be less than 4 gigs. So if I bumped it up to 8 gigs or something like that, it probably would work. But I don't want to do that. I've got some very good empirical evidence here showing this behavior. 20 years versus 2 minutes. Is there a contest at all? Absolutely not. So what we need is a way to quantify this stuff, not just empirically, because every time I run an algorithm or use a data structure, I don't want to have to set up a bunch of experiments and say, okay, well, I'm going to predict that this is bad, and I'm going to show that it's bad, right? I want to do this from a scientific point of view where I can analyze an algorithm or analyze a data structure and then have a theoretical point of view for why it's bad, right? To do that, let's go ahead and start with this example, right? Let's think about why that linked list is bad, right? So I'm going to measure out these iterations, right? On the first iteration, I'm doing a lot of work to retrieve those elements, right? This get method right here. I need to get the ith method. So I'm going to be doing a bunch of traversals. Think about your linked list here with just 3 elements, and then it goes on, okay? On the first iteration, I get this first element. How many traversals, node traversals, do I end up doing? At least on this first iteration. 0, because it's right there. On the second iteration, I have to start at the head and then traverse here. So that counts as 1. On the third iteration, I have to traverse here, to here, to here, to get it. So 2 traversals. Do you start seeing a pattern? On the fourth iteration, how many node traversals am I going to do? 3. Dot, dot, dot. On the ith traversal, how many traversals am I going to end up doing? I minus 1. How many iterations are there? Well, if there are n elements, then the last iteration is going to be n, and therefore, how many node traversals are there? N minus 1. So what's the grand total of all of these things together?
Too much.
Too much.
N squared.
Oh, good. Well, n squared, because that was already what I presented, right? But let's go ahead and use some math here. Right? Because we want to come at this from a mathematical perspective. Right? There we go. So first of all, what about that 0? Should I worry about that? No. Let's go ahead and get rid of that.
Start
At 1, right? 1 plus 2 plus 3 plus 4, right? This is going to be equal to a summation of I, starting at 1 up to n minus 1 of I. We've seen this notation before, hopefully, right? The summation, all right? Have we seen this formula before?
Series.
It is a finite series.
Yeah.
So there's this guy called Gauss, right? Gaussian elimination, Gauss distribution, Gauss, right? In a normal distribution. And the apocryphal story goes, I think it's been shown that this story is not accurate. It's just a story that people tell. That his tutor or whatever, he was annoying his tutor, and so he gave him some busy work. He said, go off in the corner and sum up the numbers 1 to 100, right? So in other words, 1 plus 2 plus 3 plus ... plus 100. And he came back immediately, having not done really any work, and said 50-50, and he was correct. Why? He came up with a formula that has many different proofs, but the sum of natural numbers from I starting from 1 up to n is simply equal to n times n plus 1 all over 2. And so when he was asked to do 100, right, all he did was come up with this formula, then he put 100 here. So 100 times 101, but divided by 2, that means that it's 50 times 101, which is 50-50. Right? So that's Gauss's formula, right? And we'll put that off over here to the side. It comes up all the time in algorithm analysis, because anytime that you have a loop that kind of has a loop within a loop, right, then you are doing something quadratic. It's probably going to be captured by Gauss's formula. Now here, we're not going all the way up to n. What are we doing? We're going up to n minus 1. So I can take this and I can plug it in here for n, and I get that I've got n minus 1 times n minus 1 plus 1 all over 2. What happens to that plus 1 minus 1? It goes away. We'll put it first. N times n minus 1 all over 2. Right? Now if you expand that out, what do you get? 1/2 n squared minus 1/2 n plus 0, which looks like a quadratic equation, quadratic polynomial to me. Right? It's not 1/2 in our quadratic regression. Why? Because we were measuring time. We were measuring the number of seconds it required that program actually took. And it's not going to take 1/2 of a second to do one summation. There's another constant sitting out front. There's another constant sitting out front here telling you that that's the number of seconds it takes for one summation. Now look at this equation right here. In fact, let me go ahead and copy it and take it over. Come on. Copy and paste and expand. All right. So first of all, should I be writing at 0? I just did that because I wanted you to drive home the point that it's ax squared plus bx plus c, right? Now what about that lower order term right here? Does that really matter in the grand scheme of things? Probably not. Let's go ahead and eliminate it as well. Now I already told you that there's some unknown constant out front here that is dependent on the hardware that you're running, that tells you how many seconds each operation takes. So if I took that c and I took that 1/2 and I shoved them together into some other unknown, is that other unknown really all that important? Probably not. What's really important here is what? That n squared. Now why is it important? Let's go ahead and think about this in terms of algebra. This n is my input size. This is the size of the array. If I go from n to 10n, say, then what's the behavior of my time? If it took time t on an array of size n, what time does it take now? If this is capturing my notion of time, it's going to be 10 times as big, all squared, which is equal to 100 n squared. And it was n squared before, so it is 100 times slower. Right? That matches exactly our empirical analysis over here. Right? Look at it from another perspective. I assume that we have calculus, yes? With calculus 1. How do you capture the notion of a rate of growth? Yep, the first derivative. So tell me about the rate of growth of something that behaves quadratically. N squared. What's the first derivative of this? 2n. Good. In other words, it's linear. The rate of growth is linear. Now let's come back over here and realize that when I did this with an array list, it was linear behavior. So let's compare that to an array-based list where it's just n. What's the rate of growth of that? Constant, 1. So the rate of growth, are these comparable at all? No, one's constant, one's linear, right? So these things matter, either from the perspective of it being 100 times slower, or from the perspective of calculus telling you that that the rate of growth is orders of magnitude greater, or from our empirical results here telling you that it will take 20 years to sum up 1 billion integers, which is not big data at all. Right? So what we need now is a framework to unify all this. Right? Because it should be clear that programs require some sort of resource to run. Before we think about a framework for doing this, tell me, what kind of resources have we already seen a computer take? Actual time or CPU time, right? What did I run out of over here? Memory, okay. So that's another resource. Those are two obvious resources. Most of you are computer engineers, so when you think computer engineering, what is your bottleneck? What is your cost? What is your resource that you're doing circuits, right? Not yet? Okay, well, you'll eventually do circuits. All right, so for your circuits to work, what do you have to do? You have to turn it on, right? So, power supply, right? Power.
I already said power.
Oh, you did? Okay, sorry, I didn't hear you, right? All right, so power, or power consumption. And the classic example that I give, or the relatable example I give, is phones don't need to be much faster, right? Every phone now on the market is fast enough for anything that you'd want to do. So would you choose a new phone that is twice as fast, or a phone that has half the power consumption? Probably half the power consumption because it's fast enough, right? That's an engineering idea. If you're doing networking, network bandwidth or throughput. Bandwidth is how much you can fit through at one time. Throughput is how much you can shove through over a period of time, right? And circuits, eventually, when you start doing circuits. I thought you did circuits. I thought you played with an Arduino at least.
Oh, yeah.
Okay.
Sorry, yeah.
Okay. But you're not doing breadboard stuff yet.
We do a little bit with that. We don't start like getting into the detail and designing our own until next semester.
Okay, you haven't even put together like a NAND gate or something?
Oh, no, we have.
Okay. Yeah, you've done more than I have then already, right? And so what's your consumption, or what's your consideration there? Why do you do NAND gates? That's a good question. Why don't you do and or gates? Why is everything a NAND gate?
Manufacturing simplicity.
Simplicity because it's wires or gates, right? Fewer wires, fewer gates means less power consumption, smaller chips, and more that you can fit on a die. Right? Those are your considerations. One consideration that you probably never thought of is idleness. And the example that I've been giving this year at least is a classic joke on, say, Reddit or something like that. You spend $5,000 on a gaming PC, and then you only play Minecraft. Did you really need that much power to play Minecraft?
I don't need to ray trace everything.
That's the answer I get from everybody. Yes, we do. But basically, you've overspent on your hardware, right? It's low utilization, right? So, I mean, this is what virtualization is all about. Where, you know, you buy a $15,000 server PC, right? And you're serving a website that only has like 100 users, right? You've wasted a lot. So what if you bought that $15,000 beefy server hardware, but then you virtualized it? You put 50 virtual machines on it. Now you are serving 50 different servers, right? You're 1/50th of the cost because there's only one physical server. But each one of them is low utilization, therefore the machine itself has high utilization. Right? Yes, there's more power consumption. Yes, it's using it, but you're not wasting money, essentially. It's another way of thinking about how to do these things. Right? These are all super important engineering concerns and considerations, right? But it's not something that we want to think about in terms of abstract algorithms. Algorithms are abstract, right? They are thousands of years old, right? Yeah, there we go. They're thousands of years old, right? For example, one of the very first algorithms was by Euclid, Euclid's GCD algorithm, the greatest common divisor algorithm, where you take two numbers and you want to find their greatest common divisor. You divide one by the other, take the remainder, divide that, take the remainder, divide that until you get down to 0. And once you've done that, you found the GCD. 2,500 years ago, it took the same exact number of divisions to do this on a piece of papyrus, or whatever the hell they used back then, as it does a computer in 2023, right? The same number of steps. Now, a computer can do those steps much faster, those individual steps, but the same number of steps are there, right? The algorithm has not changed, right? We want to view our algorithms, efficiencies, algorithms efficiency, in abstract, general terms, not in terms of any specific hardware or software. Because you could always take your, I don't know, 3080 Ti, our VR machine still has a 1080 Ti because it's almost 7 years old. But the Carson Center ones have a 2080 Ti's, I think. And of course now we're on, what, 4080s? 4080s. So you can always upgrade your hardware and make it faster, right? But you're only making individual steps faster. You're not making the algorithm any faster. The behavior and efficiency of an algorithm is invariant over time and over the type of hardware that you use, software you use, whatever, right? From a theoretical perspective, we want an abstract notion of what that resource means. And so we're not going to be looking at actual CPU time, memory, power consumption, whatever, right? We want our framework to be abstract. What matters is the performance as the algorithm processes larger and larger and larger inputs. In other words, what's the behavior when we go from 1,000 up to 1 million? When we go from 1 million up to, or to a billion or whatever, right? We want to look at the behavior of that. We want to look at it from this perspective, right? Is there quadratic growth? Is there linear growth? Is the growth flat? That'd be great, right? If we got like a constant time algorithm. Algorithms are independent of the hardware that we run them on, right? They predate modern computer by thousands of years. Algorithms do not suddenly become efficient because you upgrade your hardware. And individual operations do become faster and more efficient, but the number of operations stays the same. So therefore, the rate of growth of an algorithm remains invariant regardless of the hardware. Larger input leads to slower performance because of more resources. We want to capture this intuitive notion. To be able to even do that, we need to be able to talk about algorithms independent of any programming language. And therefore, we introduce pseudocode. Pseudo being Latin for fake, right? Fake, not fake code, right? Have you seen pseudo, like, usually in intro computing courses, like say in high school or even just, you know, math courses, will introduce the notion of a flow chart, right? Kind of the same thing. You've done flow charts before?
I did a lot of the beginning semester.
Oh, really? Why?
Sorry, assembly, for assembly.
Oh, okay. All right. All right. A whole course?
No, we
I
didn't.
said we
Oh.
didn't.
Oh, okay, all right. Yeah, you wouldn't want to. Oh my God.
There were flowcharts.
So an algorithm, if I just pull out Webster's dictionary, an algorithm is an unambiguous sequence of instructions for solving a problem. That's the dictionary definition, right? If you get into real computing, like theoretical computer science, you will not, this is not a sufficient definition. A definition for what an algorithm is either a Turing machine or lambda calculus, right? But this definition is good enough for us, at least for this module, right? An algorithm is not a Java program. It's not a Python program. It's not a C program. It's not a C function. It's not a snippet of code at all, right? Can I give you rules for what good pseudocode looks like? Pseudocode.
Be consistent.
Okay, that's a good guideline, but what if I gave you hard and fast rules? No, that's illegal pseudocode, or that's correct pseudocode. If I gave you rules, what would I have?
Code.
Code, right? What's Java? Java is a set of rules, syntactical rules for writing a Java program. If you have rules, you've got yet another programming language. So I can only give you guidelines, right? Good pseudocode makes use of plain English when appropriate, makes use of good math notation, right, when appropriate, doesn't use any specific, any language-specific constructs, So for example, we're not going to have semicolons at the end of each line. We're not going to have opening, closing curly brackets. We're going to use something else. It provides necessary details without too many unnecessary details, right? So again, that's we call that the Goldilocks zone. Why Goldilocks?
Just right.
It's just right. Not too hot, not too cold. It's just right. Right? So for example, what if I gave you pseudocode to sort something, sort a collection, and I said, sort A. There's my pseudocode. Is that enough details for you to actually write an algorithm to sort something? No. That's not in the Goldilocks zone.
That's
What if I gave you assembly? Load the first one up into register 5. Load the second one up into register 6. Compare register 5 to register 6. If register 5 is less, then jump to memory location
Say
4.
if.
Right, if?
Oh, we wish.
What?
Love an
you
if.
don't.
Oh, you could, well, conditional jump, right? All right?
It's true, but it takes like 4 different steps. Just do like, if this
In
equals
MIPS?
that is like.
Oh, okay, well, yeah.
totally different.
That you, well, then why don't you just put that into a subroutine in assembly?
Oh, that's exactly. what
Okay,
it
all
is.
right, all right.
And then it's 4 steps to call that subroutine.
Oh, okay. Well, I mean, that would be too much on the other direction, right?
Yeah, something
So you want,
is meant for something.
you want something in that Goldilocks zone, right? Where you don't have to worry about the details, but you need the details in order to translate it to Java, or translate it to Python, or translate it to assembly. Yeah, I wouldn't do it at that point. Anyway, let's go ahead and look at an example here, a real example, right? So, let's go ahead and do, I don't know, no, let's go ahead and do find the max. Find the max value in a collection of what? I don't know. Let's start by writing good pseudocode. We're going to identify the input and the output first. Input. A collection of elements A equals A1, A2, dot, 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 AN. Right? Now, before I even go on here, let's understand why this is good pseudocode. Did I say that this was an array? Did I say that this was a list? Did I say that this was a Python list? Nope. What I said is this is a collection of elements. Right? Now, mathematically here, the mathematical notation here says that this is indeed a set, but that's okay, right? What else have I done? I've given them each a name. A1, A2, A3, dot, 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 AN. What have I not done that almost every programming language does? I've not indexed them at 0. Right? Why not? Because this is math. This is a pseudocode. Not every programming language does that, by the way. R, have you ever heard of R? It's a statistical programming language for statisticians that don't know how to program. Have you ever heard of MATLAB? Probably.
Yeah.
Yeah. Oh, have you used it?
Just a little, like.
Okay.
What's
What's its indexing?
we didn't have to work with the next.
Oh,
one.
okay.
So it's one since you're bringing it up.
It's 1, exactly. Right. MATLAB is matrix. A bunch of it's for engineers and that don't know how to program, just like R is for statisticians that don't know how to program.
Thanks, that's so enlightening.
It's C-style syntax. It's written mostly in C. MAT stands for matrix manipulation. It's mostly for solving systems of linear equations,
Yeah.
solving systems of differential equations, partial differential equations, et cetera, et cetera. Right? It's more of a tool than a programming language, but it is a programming language. Right? Oops. My output here is going to be the maximum value. In fact, I'll say maximal value in A. Did I say that these were integers, doubles, strings? No, I just said that they were things, elements. Because you can have a concept of maximum with respect to, say, invoices, right? An invoice has a total, and so compare that invoice to that invoice, their total or number of sales or the salesperson, right? They all have different notions of maximum. Why did I call it maximal instead of maximum? So here's an example. 1, 7, 8, 9, 9, 4. There we go. What's the maximum value there? Technically nothing. 9 is maximal. Why? Because there are 2 of them, right? So, who cares about that, right? That little definition. That's why I'm saying it's maximal, okay? All right, help me out. For each A in A. Say what?
Isn't that Java specific syntax?
No, it's plain old English to me, because there's no, each keyword, right?
Oh, that's
And,
true.
and in fact, I only know of one programming language where there is a for each keyword. It's one word. It's PHP. Even Python, you would do this using a list comprehension, and the each keyword never applies. So for each A and A, now this is something specific. I'm not going to use the colon here. That would be very Python-y. I am not going to use, I'm not going to use opening and closing curly brackets and parentheses, because that would be very language specific. I am not going to use a traditional idiomatic for loop here. For int I equals 0, I is less than n I plus plus. Why? Because I want to keep it general and generic. Okay, I could do this. Well, I could use summation, if I were doing the sum, right? I could do like sum of A in A of A, right? And there's the sum, but I'm not doing the sum, I'm finding the maximum, right? All right, so if A is greater than what we found so far, max, then I'll go ahead and update max. What did I do there? I did not use the equal sign. The equal sign is not universal, right? If I say n is equal to 1 million here, right? Go back in time to when they started first developing programming languages and hit them over the head, because they should not have done this anyway, right? Why? Because in math, this has a very well understood meaning. The thing on the left-hand side is equal to the thing on the right-hand side. It was a mistake to make this into the assignment operator. Not all languages do that. Some languages use that. Maple, Fortran, I want to say. Anybody know? What about assembly? Do you have an assignment
There
operator
is
there?
no-
No. Just load into register whatever, right?
Load
Uh,
immediate.
There's a programming language called Haskell that does something like this. You shouldn't be using variables in Haskell anyway, but you can do something like this. What is that doing? It's an arrow that says, take this thing and put it into this variable over here.
Why
Right.
don't you like
Nice.
equals?
What? I don't like,
You like
I don't care.
equating that
Because that's math, right? Why did we steal this idea and then pervert it from the mathematicians, right? And then that gets into the whole issue of, well, what if you do want to test equality? Now you need to use two equal signs. What if you've got a dynamically typed programming language and you need strict equality? JavaScript, PHP, 3 equal signs. Yeah. And so you're creating a whole bunch of problems 50 years later by not using something that makes sense. And you're not using something that makes sense 50, 60 years ago. Why? Because you were stuck with the QWERTY keyboard, which predates modern computing by 100 years or whatever, right? And so therefore you're stuck with whatever's on the QWERTY keyboard. Right? I'm going to go ahead and fix that by only using a left arrow here. Right? Okay. I'm not going to use indentation by itself, and I'm not going to use opening and closing curly brackets. Instead, I'm going to make it so that I'm doing something that you cannot do in any programming language whatsoever. I'm using these vertical lines with this little tiny indentation thing here to indicate that the block begins here and it proceeds down to there. You actually see this in modern IDEs. Here's my main. If I hover over this thing over here, what do you see? Yeah, a collapsible vertical line with a little tiny indentation over here to indicate that it ends down here. That's so that you can collapse and expand. I like using this style over here because you cannot repeat this in any language that I know of. You can kind of get it in an IDE, but not, yeah, it's not a language. Output, max. Did I say return? Did I say system.out.println? Nope. I just said output max because that's the end of the algorithm. I left some space up front, up at the top. Why? We don't have a starting point here. Right? Is everything going to be greater than max?
No.
Nope. So what value could I initialize max to here to ensure that anything will be greater than max?
Negative infinity.
I like that. Why? Good mathematical notation. Right? You can't do that in any programming language. You could do math.inf and initialize it there, but or math.negativeInf, but you can't get the infinity symbol anywhere.
Yeah.
I wonder if I.
Unless you somehow add negative to each of the negative.
Oh no, that's not gonna work. There.
Would that even be smaller?
Those are not defined. Just like 0 to the 0 is not defined. Right? Or x divided by 0 is not defined. I also like going through and numbering my lines because I'm going to make reference to them. Okay? There's some good pseudocode. Right? I don't know how to make that any more general. Now, the reason that I go with this, this style here is also because it's supported by LaTeX. If you're writing algorithms in Algorithm 2E environment, you can set it up so that it looks like this. A lot of this stuff might be default anyway. But unfortunately, if I gave you those as rules, guess what? It's just a programming language. You're programming in LaTeX. LaTeX is Turing complete. You can write anything that you want in LaTeX. You've got loops, you've got variables, you can do whatever. You don't want to do it, but why would you want to do it? You wouldn't want to, right? All right, so once we've got our algorithm, right, we need a way to analyze it. And I'm going to give you a 5-step process here that we're going to go over a little bit today. 1, you identify the input. 2, you identify the input size, and generally we call it n. Those two are super easy. if you've written good pseudocode. Why? What's the input over here? What's the input to this algorithm? The collection A.
Would you wanna throw a line of pseudocode in for that, or just so that you have it,
Well,
they give it written at the top?
yeah, I've got it written at the top. That's, writing good pseudocode means writing input and output. Sometimes these are called preconditions, postconditions, whatever. But writing good pseudocodes means that you've done that. What's the input size here? I've also encoded that as part of the input. It is n, the number of elements in the collection, right? Why do we use n? Why, in fact, why did I use that up here? Why was I using n instead of x?
Number.
Number, okay. When I say x, what does it bring to mind?
Algebra.
Okay,
Like math.
math and the x and y axis, right? So when I say, come on, all right, fine. When I say x, what kind of numbers are you thinking of? 1, certainly. 2, 1.5, right? Pi,
Oh, sure.
right? In other
Any
words,
number, not integers.
real numbers, not integers. So why am I restricting myself here to n? Have you ever heard of an array or a collection of 3.5 elements?
Which language has that?
None. Have you ever heard of an array of 7.5 elements, or an array of pi elements? 3.14159 elements?
No,
No.
because you can't have half an element.
Exactly, that doesn't make any sense.
Just
So
like,
we're going to restrict this to integers. An input that, you can have an input of size 0, an input of size 1, 2, 3, 4, dot, dot, dot.
it's kind of like how the average household is impossible because
Exactly, 3.5 children, or whatever it is,
Yes.
2.7 children. Hopefully that's going down. But I also am not I'm restricting my attention to positive or non-negative numbers. Why? Can you have an array of size -10?
sure, no.
No. So that gives us rise to the natural numbers. The natural numbers are 0, 1, 2, 3, dot, dot, dot. So not even integers, because we don't want negatives. Okay. Okay? So that's why I'm using lowercase n here, because natural numbers, n. It tells you that it's going to be an integer value, integral value. Okay. The third step, you need to identify the elementary operation. Now the elementary operation, in a real computer, you're doing register loads. You're doing cache hits and misses. You are loading from main memory. You are doing register jumps, et cetera, right? In an actual high-level programming language, the for loop here has an initialization statement that's executed once. A comparison to see if you should keep going. It's an addition, right, to see if you, to increment towards this next condition. It's got a get method, et cetera, et cetera, et cetera. Focus on one thing, right? You don't want to focus on too many things here, okay? So in this case, what is our elementary operation? It's the most important or the most common operation? Is it this output right here? No, that's just done once. Is it this initialization? It's only done once. Definitely want to focus on this for loop here, okay? Do we want to focus on anything that's necessary for the control structure of the algorithm? Probably not. Again, why? You're doing something inside that loop. That's probably more important than just doing the loop itself. So now let's focus on lines 3 and 4. Is line 4 always executed?
No.
Nope. So what's more common between 3 and 4?
3.
3. The comparison on, then this is why I like lining the, line numbers. Because you just say comparison, line 3, done. All right? So, step 4. Determine how many times the elementary operation is executed with respect to the input size. We already did this with our demonstration over here. We came up with a quadratic polynomial for it. This one's going to be even easier, though. N. Why?
Tell us that, what's the size?
For each, when we do this for loop how many times for each element here? How many elements are there? N. And so we execute this n times. It's not always going to be that easy. We might have to set up and solve a summation, but there you go. 5 is going to be for later. We'll fill this in later, but this is going to be order n. If you consider this as a linear function, the time that it takes to execute this algorithm is some an plus b. Remember these lower order terms, who cares? Remember this coefficient, who cares, because you can always upgrade your hardware and now it's a divided by 2. Right? What really matters here is this n, and that gives us big O of n. We talked about big O already? No? Okay. We'll do it later. Okay. Let's look at some subtleties on the first 3 or 4 steps here, though. Okay? Identifying the input is pretty easy, right? Except when it's not. Generally, this is given as part of your pseudocode. In some cases, the choice might not be clear. Keep it simple. Focus on one of the inputs if there are multiple inputs. Focus on the most relevant input that may affect the runtime of your algorithm. For example, linear search. Do you actually you remember linear search? Here's your array, here's your key. Search this array for that key and the needle in the haystack. I have 2 inputs here, a key and then an array or a collection. Which one is most appropriate? The collection, because it can grow in size. And there's only ever one key. Euclid's GCD algorithm takes 2 integers, right? Instead of considering both of them, you can say wlog, assume that a is greater than or equal to b. If not, then just swap them. It doesn't change the GCD. And then consider a as your input. Wlog is math without loss of generality. Right? Yeah, the mathematicians do that all the time. Without loss of generality, make this assumption because that assumption makes our arguments easier. And that assumption applies to everything. Right? Assume that a is greater than or equal to b. If not, just swap them. Right? Yeah, and then if you really, really wanted to consider both of these as your input, fine. The number of bits over here, the number of bits over here, if this one is less, then it's at most this many bits. So if it was 10 bits, 10 and 20 bits, it's at most 40 bits, right? So just swap them. Identify the input, keep it simple, keep it to 1. That brings us to the second step, which can also have some subtleties, identifying the input size. Right? It is subtle, but important, and may be tricky. Right? For example, there are things that are straightforward. Right? If a collection, then the size or cardinality. Have you heard that term before? The cardinality of a set? No? Okay. If you take discrete math, you eventually will. Right? I don't know if you take discrete math or not. Right? If the input is a matrix, right? An n by m matrix, what's your input size? N times n, c dot m. Again, without loss of generality, right? Assume that n is greater than m. How does that simplify things? Input size is at most n squared. Now you're down to 1 variable, right? 1 variable is good. 1 variable is better than 2 variables, better than 3 variables, certainly. Then substitute. N is equal to n squared. And now you're back to 1 variable with no square at all. N, big N, is now my input size. Right? These are just little parameter tricks that you can simplify your arguments with. Right? What about an image that is n by m pixels? Right? Same argument. Just make it a square image, because if it's not a square image, if it's this rectangular image, pad it out with a bunch of black dots, right? So now it's a square image. Now it is n by n, right? And now you just go ahead and say, well, how many total are there? There are n squared. Just call that your input, n. Right? If it's 1,000,000 by 1,000,000, then now, well, no, the input size is now, what's 1,000,000 times 1,000,000? A trillion, right? A trillion, there we go. Just one number, right? Just one value. Here's the tricky part, though. What if your input is an integer x, I'll say. Or let's make it confusing. What if the input is an integer n anyway? Is that the size of the input?
No.
No. What would I be doing there? My input is, say, 5. So is the input size also 5? Did it take me 5 things to write that down?
No.
No. 1, 2, 3, 4, 5. There's what I would be doing if my input size was 5. If my input size were 9. 1, 2, 3, 4, 5. 1, 2, 3, 4. Have you seen that style of counting before?
Yes.
What's that called?
Tally.
Oh, tally or unary,
Oh.
right? One symbol and one symbol only. Nope. Unless you're stuck in a prison, right? That's the trope, right? People have, you said tally? Oh, tally's on the wall or something like that, right? Okay. So if I gave you x, what is an integer? What is the size of the input?
1 or 4 bytes. Or
Okay, you're already jumping to the conclusion of bytes, of bits, right? And that's exactly right. There is a difference between 1,234 and 8,734,509, right? In the first instance, it took me 4 characters to express this. In the second instance, it took me how many? 7 characters to express this. So we don't compute in base 10. Well, I mean, computers don't. We do as humans, right? But computers don't have 10 characters. They have 2 characters. They certainly don't do unary, right? With only 1 character. That would be extremely inefficient. Right? So the question becomes, how many bits does it take to express x? Right? That's the input size. So if I gave you x, how many bits does it take to express x? All right, good. Let's think of in terms of base 10. And we'll go in reverse here. What if I gave you, say, digits instead? So number of digits, max value expressible. Right? What if I gave you 1 digit? I'm not allowing you 2 digits, so you can't do 78 or something like that. I only gave you 1 digit. What's the maximum value that you can express?
9.
9. But what if I gave you 2 digits?
9.
99. 3 digits?
900.
99. Dot, dot, dot. What if I gave you, here, I'll go with k here. K digits. See the pattern now? What is it going to be? Well, 10 to the k minus 1. Why minus 1? Because you got to start at 0. Right? Now, continue. Suppose that I had a number n or x. I need to go backwards. Right? So, how do I find out how many digits it takes here?
Log 10.
Okay, good, good. Log base 10 of n, and then ceiling that or something like that, right? We'll ignore that ceiling, but there you go. Why? Because if you solved for this, if I said x is equal to 10 to the k minus 1, or n is what I was using, sorry. Solve for k. What do you do to that negative 1? N plus 1. Now what do you do to get rid of this 10 right here? Log base 10. There's k. Right? I'm ignoring that plus 1, and I'm ignoring the fact that we would have a ceiling here. Because if I said that it takes at least 7.8 digits to express that number, then you need 8, right? Okay, same exact exercise, but now you're not thinking in terms of human computers. You are thinking in terms of computers. Right? So if I gave you bits, what's your maximum value? So if I gave you 1 bit, 1, which is equal to 1. If I gave you 2 bits, 1, 1, which is equal to what? 3. 3 bits, 1, 1, 1, 7, good. Oh, we know how to count in binary? Okay, good. This is gonna be what? 15, right?
I was gonna say F. That's
Oh, good answer. That would be F then, wouldn't it? Well, you need to
exactly.
oh, X, F, there we go. Excellent. Now you are thinking about assembly and C. Excellent. All right, so what did I use over here? K. What if I gave you K bits? And by the way, we call them bits, but the original name was digits, right? But that sounds weird, so binary digits, and so they've shortened it to bits, thankfully, eventually. Right? What's the maximum value that you can express here? Well, it'd be 1, 1, 1, 1, dot, 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 1, 1. There are going to be K digits here, which is equal to 2 to the K minus 1. Exactly as before over here, but it's a different base. So once again, solve for n over here. N is equal to 2 to the K minus 1. N plus 1 is equal to 2 to the K. What do I do to get rid of that 2? Log base 2 of n plus 1. So over here, I'll just say log base 2 of n. That's the number of digits, the number of bits it takes to represent an arbitrarily large integer, okay? And it is important, right, for the number of bits required to represent the number, and that's going to be log n. Let me show you why it's important, and this is going to be our last exercise for the day. Have you ever heard of Eratosthenes?
No.
Okay. So 783, there we go. Is that number prime or not?
Oh, no idea.
No idea? All right, so how do you go about finding that out? 2. Does 2 divide it? No, because it's not even. 3. Does 3 divide it?
Not sure.
I'm not sure either. 3 would divide the lowest order digit. And
Yes.
then it does? Okay, darn it. All right. Then we got lucky right away. All right, fine. 1. 7, 8, 3, 1.
No.
Nope. Okay. So next 4, we don't have to do that because we already did 2, which is a factor of 4. So we only have to do primes. 2, 3, 5. Definitely not because it doesn't end in 5. 6, 7.
No.
Nope. Okay. I'm not going to do it all, but when do I end? I don't have to go through all the way to 7, 8, 3, 1.
No, halfway.
Halfway with
No.
respect to
Ooh. The number you
the
start
geometric mean,
with. Right.
which is the square root of n. Right? Because any factor that you find after that is going to have a corresponding factor up here.
Right.
So that suggests the following algorithm. That it's kind of the sieve of Eratosthenes, and not strictly speaking, it's not. But it is, input is a number x, right, which is an integer, Right? In fact, let me go ahead and just call it n here to make it confusing. My output is going to be a factor of n if not prime. Not prime being composite. All right? So for each prime p in 2 to the square root of n, if n, or here's the actual mathematical notation, p divides n, right? Then output p. Right? So this is p divides n. Right? Or how would you do this in code? N mod p is equal to 0. There we go. All right. What is the elementary operation here?
Division.
Division. All right, I would buy that. How many times is it executed?
Square root of n. No.
Yeah.
UL.
Yeah, it is square root of n.
Oh.
Um, taking out non-prime factors. Right? We'll just say that it's about that. Oh, so it's better than linear.
Yeah.
Mm.
Fraction of, yeah.
Yeah, why? Because this is less than n. Right? Nope. What was our input size again? Our input was n. Our input size is what? Log n, right? Log base 2 of n. So square root of n is equal to, in terms of the actual input size, let me give that a different name, big N. So therefore, little n is equal to 2 to the big N. And therefore, this thing is 2 to the big N of n. Does that look polynomial at all? No. That's exponential. The sieve of Eratosthenes, or our version of it anyway, is definitely not better than linear. We hid that fact from you by not identifying the input size correctly. But if you do the input size correctly and say that it's log base 2, right, then you get the true sense that it is exponential. Right? Try it, implement that sometime and for a very large number, and you'll find it's going to take a long time. Right? And by the way, we're self-respecting computer scientists. All of our logs are base 2, right?
What?
All of our logs are base 2.
Since when?
Since now, because we're computer scientists. Why? When we write log of n, the implicit base here is 2, because everything is binary. Does it really matter? Change of base formula. Log base b of x is equal to log base a of x log base a of b, something like that. I don't remember if that's it. I don't remember. Whatever it is. Whatever the change of base formula is. Self-respecting computer scientists will always have an implicit base 2. Why? Because of binary. Self-respecting mathematicians don't have that base. What is their base? Nope.
Or the natural log.
The natural log. Why do they call it what the hell is natural about
Because it uses
e?
which is
E is what?
x.
2.71 dot dot dot. Well, 2 is exponential. 10 is exponential, right? 2 to the x, 10 to the x. What is,
E
there you go. E to the x. Derivative of that is what? E to the x with a 1 out front that we don't write. That's why a mathematician would consider it natural, because that coefficient goes away. If you use, say, 2 to the x, what is the first derivative of 2 to the x?
Oh, no. It's, yeah.
No, 2 to the x. There we go.
There we go.
There's a natural log of 2 sitting out front because of the change of base formula.
How does
Right.
the natural log, what's the other? You want the net is what?
2 to the x.
No.
Yep, right there, right? So mathematicians, self-respecting mathematicians, will consider this to be natural. Computer scientists consider what to be natural? Binary, because that's what all our computers are. Does it really matter? No, because you can take our base 10 system, because we've got 10 fingers and 10 toes, and translate any number into binary. You can take our 10 fingers and 10 toes and translate them to base 13, right? So for some alien language or some sort. They've got 13 fingers instead. It doesn't matter. But can you do that with E? Is there such thing as a base system with 2.71 symbols?
No.
No. Theoretically there is, though. There it is. E. You can't write it just like you can't, diagram a 4-dimensional object, right?
Well, it's fun to know with that attitude.
we don't, I don't know. So, by the way, there are theoretical computer science models that operate on real numbers, and like trippy things happen with them, but it's all theoretical. It's not real.
What do you mean by that?
That you don't consider bits. Instead, you consider like a real number. You know, it's infinite, right, and not repeatable. But suppose that you could write it down, right, and then operate on an infinite sequence of values. What can you do then that you can't do when you're restricted to 64 bits?
Feeling modern encryption just goes out the window?
No, not much happens actually. That's why it really didn't go that far. It's the Bloom-Schubs-Mail model or something. I forget what it is. But anyway, there are also